Thank you, Elizabeth, and thank you to you and to the other organizers for the invitation, and thank you to everybody for coming to hear. So I'm going to be talking about some recent results about a quantity known as magnitude, which in general is associated to a metric space. So I'm going to start with a definition that applies in arbitrary metric spaces, and I'll move on to subspaces of L1 eventually. So let's say I have a metric space X and a signed measure. I emphasize signed is important here. It is called a weight measure if it has this property that if we integrate negative exponential of the distance, we get 1 for every point, fixed point in the metric space. So if X possesses a weight measure, which might or might not be the case, then the total mass of the space X is referred to as the magnitude of the metric space. So one very quick example, because I'm not going to have many concrete examples for the next several slides, is a compact interval possesses a weight measure. It's basically Lebesgue measure together with point masses on the endpoints with appropriate balancing of the weights. And you can calculate that the magnitude is 1 plus half of the length. So whatever this quantity magnitude is, among other things, it knows how to determine the length of an interval. I'm also going to want to think about rescaling metric spaces. And when X eventually is mostly a subset of a normed space, I can multiply it by a scalar t and it means what you think it ought to mean, but I'll want to talk about that for more general metric spaces as well. And so I just, by tx, that's a shorthand for saying I take the set X and multiply the distance by that scalar t. So if I'm looking at a subset of a normed space, it doesn't matter whether you think of it this way or in the more obvious way up to isometry.
Mark, sorry to interrupt. Hi, this is Emmanuel. Just a question about, so the measure, I guess, is unique because of like Stone versus Stars or something? It's because I had to think about this for a minute just right now. The uniqueness is because of some separation of points, right? These exponential measures are dense instead of continuous. The algebra they generate are dense instead of continuous functions, so the measure must be unique, something like that?
Well, under sufficient conditions, it will be unique. It won't always be unique, but the magnitude is always unique. It's a simple lemma that if there are multiple weight measures, they give you the same magnitude.
Oh, okay, thanks.
Okay. But it will be unique in the situations I care most about eventually. But yeah. Anyway, and then if I think about the magnitude as a function of the scaling, I'll refer to that as the magnitude function. And I should point out that the definition here has a rather arbitrary choice of scale built in the fact that I'm using one particular base for this exponent here. And so thinking about the entire magnitude function is a way of getting rid of that arbitrariness. So this notion showed up in at least 2 different independent ways in the literature before, not under this name, but essentially this idea was introduced in theoretical ecology by Solow and Pulaski back in the 90s as a way of trying to talk about the effective number of species in an ecosystem. It was later independently reintroduced by Leinster. He first publicized this in a blog post in 2008, and his motivation came from category theory. I'm not going to spell out either of these motivations, but for the sake of time, I'm just going to move right on with the definition. I will mention, though, another more recent elaboration of the category theoretic connection, which is the magnitude function is actually an Euler characteristic associated to a homology theory defined for metric spaces. So this is a homology theory that's based on metric as opposed to topological information. And it has a notion of Euler characteristic that turns out to be a function, and it is the same as this magnitude function. And this homology theory, which is called magnitude homology, has turned out to be closely related to persistent homology, which is one of the big topics in the recent field of topological data analysis. And I'm not going to say any more about any of that in this talk, but since all of this is where a lot of the most recent work on this subject has been happening, I should at least mention that. The specific form of the definition that I wrote down using measures so that you can apply it not just to finite spaces, but more general spaces, was first proposed by Willerton as a way of giving a definition that could apply to more general Riemannian manifolds. And I'm going to, in a couple of slides, generalize the definition in a rather different direction, but this is the one that I want to take as a starting point. Before I get into generalizations, let me say a bit about the asymptotics of the magnitude function, which is one of the main things that I'm going to be interested in. So for the moment, let's just look at if X is a finite metric space, then so this magnitude might not be defined, as I said, because a weight measure might or might not exist. But for a finite space, at least you can show that this will be defined for all but finitely many rescalings. And furthermore, if we scale up the space, then in the limit, the magnitude tells you what the number of points is. So keeping in mind the ecological motivation that I alluded to before, we think of magnitude as, in some sense, telling us something like the effective number of points in X if you're looking at the space at a certain scale. So if T is really big, you're making the distances really large, so you're zooming in a lot on the space and able to see individual points. If T shrinks down to 0, you're shrinking the space. It's as if you're looking at it from very far away. A little bit later, there was this theorem of Willerton, who was looking at homogeneous Riemannian manifolds. The homogeneity is a pretty significant restriction here, but that was so that he could say for sure that a weight measure exists. You can just take the Haar measure on such a space and then look at what the scaling is. And what he found is that the magnitude function of such a space knows about the volume, knows about, so TSC here stands for total scalar curvature of X. Notice that the power on T drops by 2 here. And then there are other error terms of at least 2 orders smaller. And something that fits nicely into the themes of this workshop are that the total scalar curvature here is, after the volume, the next intrinsic volume in the setting of Riemannian manifolds. So we've had at least 1 or 2 talks allude to the Weyl principle, or the Weyl tube formula, in which this shows up as one of the coefficients. But the coefficients, the dimensional coefficients here are different from what shows up in the Weyl tube formula. And that's going to be related to things that we'll see in Euclidean space in a few more slides.
Mark, is it, are there obvious relations between, like, I don't know, the size of a 1 over T net and the magnitude?
Well, what's obvious is in the eye of the beholder, but yes, there are, and I will be coming to that shortly. So to move on, I want to introduce a technical condition, which is to say that a metric space is called of negative type if the matrix of negative exponentials of scaled up distances is a positive semi-definite matrix for every choice of scaling and every collection of points that I take from this space. And okay, it's positive semi-definite. The negative and negative type can be thought of as having to do with the negative sign here. So this is a classical property that comes up a lot in the study of isometric embeddings of metric spaces. In particular, one very classical property that more or less goes back to Paul Lévy is that a normed space is of negative type exactly if it embeds isometrically in L1. In particular, little lp is going to be of negative type when p is between 1 and 2. And so our favorite examples here are when p is 1 and when p is 2. So Euclidean space and little L1 spaces are examples here. And still in the setting of finite metric spaces, one thing we can say then is, in that case, with the assumption of negative type, magnitude is always defined. Also, magnitude, in this case, avoids a number of pathologies that I haven't admitted to. There are a number of ways in which the magnitude of an arbitrary finite space can have some very odd behavior for something that I claim is an effective number of points. And a lot of those bad behaviors go away under this assumption of negative type. In particular, the magnitude is always going to be at least 1. But I don't want to focus on finite spaces. I want to move on to more general compact spaces. So the first observation is that magnitude, if I restrict it to finite metric spaces of negative type, it's not continuous, but it is semi-continuous. It's lower semi-continuous with respect to, say, the Gromov-Hausdorff topology on that family of metric spaces. And if you have lower semi-continuity, then there is a canonical way of extending to a larger family that's dense in. If I look at compact spaces of negative type, then I have a canonical maximal lower semi-continuous extension to all of those. And I have a variational characterization of the magnitude as this supremum of this ratio of bilinear forms of, again, this is looking at all signed measures supported on X. So Daniel, you asked about whether there are relations with the sizes of nets, and I'm going to come back to this at the very end of this talk. The easiest way to get a relation would be to say, look at mu supported on a net and see what you get out of this. And as I said, that will be an important point on the very last slide for this talk. Also, you can show that this supremum is actually achieved for a given measure exactly when mu is proportional to a weight measure. And you get from that that this definition coincides with the weight measure definition if you are looking at a compact space of negative type, which does possess a weight measure. We can actually give another reformulation of this definition, which I'm not going to state in this talk, where weight measures get replaced by appropriate distribution-like objects. And if I'm looking at subspaces of L1, they really actually are distributions. And in that case, they will always exist and they will always be unique. And that's going to come from a strict convexity property that you can prove with Fourier analysis. Okay, so first thing that one would like to know about this lower semi-continuous quantity is whether it's actually continuous, at least in some nice situations. So here's one result that I have. If I am looking at a fixed finite dimensional subspace of L1, and I'm just looking at the magnitude of convex bodies, and I'm emphasizing here that by convex body, I mean with non-empty interior, then magnitude is continuous on that family. it's an open question whether that restriction to non-empty interior is actually necessary. And the answer is probably, okay, so what I just said out loud and what's written on the slide have opposite answers. Probably it is necessary to assume non-empty interior. So that is, probably it is not true that magnitude is continuous on all compact convex sets. That is, that you can have discontinuity when you flatten out a body into something that just sits in a proper subspace, but we don't actually know that for sure. However, if you leave out the convexity, then the answer is definitely known to be no. It was independently found by Willerton and by Kimperlein and Goffing that if you take a spherical shell and shrink it to a sphere in Euclidean space, then you get a discontinuity in the magnitude at the sphere. Okay, so now let's talk a bit more about asymptotics. So if we look at, now I want to focus on subspaces of L1. If I look at a compact subset of L1, I look at how the magnitude scales, it's going to behave like t to the n times this multiple of the volume. So BE here is the unit ball for E. So this was proved in Euclidean space first, and then generalized in a paper that happened to get in print first to arbitrary finite dimensional subspaces of L1. So in this setting, as well as the earlier setting of homogeneous manifolds, the magnitude function knows about the volume of a set. And this is for an arbitrary compact set. In particular, this is also going to be true if the volume happens to be 0. So far, I've just talked about the big T asymptotics. What about if you shrink your space to a point? So the natural guess then would be that as you shrink to a point, you get the magnitude of a 1-point space, which is indeed just 1. So this would fit nicely again with that philosophy that the magnitude is the effective number of points. But here's a funny example, and I didn't write it down, but this is another thing due to Simon Willerton. If X is the graph shown here with its path length metric, the geodesic metric, then this is a space of negative type whose magnitude, when you shrink the space down to a point, doesn't go to 1. It goes to 6/5. So the magnitude is always bounded above 1, which is a surprising thing. On the other hand, this guy does not sit inside of any subspace of L1. It's not in L1. So we'll return to this question of shrinking to a point with stronger hypotheses soon. So the next set of things that I want to talk about are the things that we can say in L2. In Euclidean space, there is a differential characterization of magnitude. And this turns out to be the approach to most of the things that we know that are specifically true in Euclidean space. So what we know is that magnitude of any compact set in Euclidean space can be given a new variational characterization as an infimum of this. So this is a certain Sobolev type norm, looking at nice enough functions that are 1 on X. Okay, so a first thing to notice about this is this n plus 1 over 2. And this is something that falls out of the Fourier analysis. That of course, this is going to be fractional if n is even, which means that you really need Fourier analysis to even make sense of this expression. If n is odd, this is a perfectly classical ordinary, well, I shouldn't say ordinary, partial differential operator is a classical thing. But if n is even, then this is a pseudo-differential operator, and there's no making it simpler than that. So that's going to show up in some of the later things. Nevertheless, on the one hand, this is a kind of thing that makes an appearance in potential theory, and using some results from potential theory, together with relating magnitude to sizes of epsilon nets, one can show that if you look at basically what is the power type growth of magnitude when you scale up, what you get is exactly a very classical notion of the dimension of X. So if X has non-empty interior, has positive volume, the earlier results already show that the magnitude grows like some multiple of t to the n, but also if X is a lower dimensional thing, then it still grows something like t to the Minkowski dimension of X. So this is also the same type of fractional dimension that's often called the box dimension. The other thing that is known for all dimensions from this is that if you take a subset of Euclidean space and you shrink down to a point, then we avoid the pathology of that example that I showed before, that in fact the magnitude does go to 1 when you shrink. Okay. To go farther than that, we start running into that issue of the dimension needing to be odd to take a very classical viewpoint. And in odd dimensions, the magnitudes of balls were calculated explicitly, first by Barcelo and Carberry, and then by Willerton. And we get in 3 dimensions something not too surprising looking after you've seen the magnitude of an interval. But in 5 dimensions and beyond, we start getting something a little stranger. And in general, what we get is a rational function of the radius with rational coefficients, but the explicit description of it is really quite complicated. And I should say that as complicated as these are the only convex bodies in Euclidean space whose magnitudes we can say we know exactly. And calculating that is quite a non-trivial task. So let's forget about exact calculations for now and go back to thinking about asymptotics. Again, if we are willing to settle for odd dimensions and also assume a certain amount of niceness, we can go beyond this asymptotic that says the magnitude grows like the volume times t to the n, but we can identify the next couple of terms. We get next some multiple of the surface area. After that, some multiple of, this is the integral of the mean curvature. So that's the average of the principal curvatures on the boundary. And then the result is stronger than what I've stated here. There is an asymptotic expansion in powers of t. All of the coefficients are going to be related to integrals of the curvatures, but writing down what they are explicitly becomes harder at each step. But again, these are rather familiar coefficients to many of the people in this audience, so I'll get more explicit about on the next slide. But the other thing is that using the greater strength that I didn't quite state in this first result, they also showed that if we have 2 sets that are nice enough, then we get an asymptotic inclusion-exclusion principle for the magnitude, which is a nice thing to see holding even approximately for something that claims to be some kind of notion of size. So we get that the magnitude of the union plus the magnitude of the intersection is basically the magnitude of the 2 sets added together, at least asymptotically if we're blowing up. Okay, so both of the results on the previous slide will make many of the people here think about intrinsic volumes. So intrinsic volumes have already appeared many times this week. So let me just give a super quick review of the aspects that are most relevant to this particular talk. So intrinsic volumes are functionals V0 up to Vn, if we're working in Rn, which you can characterize. So this is something that's really in Klein's approach to proving Hadwiger's theorem. Vi is the unique, up to appropriate normalization, isometry invariant valuation on compact convex sets. So by valuation, I just mean something that satisfies inclusion exclusion when all of the sets here are convex. So it's an extra hypothesis that the union here has to be convex. And for the uniqueness, we also need to specify homogeneity as well. And these also appear in the Steiner formula. So this is the convex geometry counterpart of the Weil tube formula that I alluded to earlier, that if I look at K and I look at the parallel body, so that is I blow it up a bit by adding a multiple of the Euclidean ball, then I get something which is a polynomial in the radius of the ball here, and these intrinsic volumes show up as coefficients there. And another perspective, which is relevant to the first result on the previous slide, is that these can be given as, well, once we get past the top one, which is volume, as integrals of the curvatures, integrals of functions of the principal curvatures on the boundary. So surface area is the next one up to an appropriate constant, and the integral of the mean curvature, and here I'm not saying what the coefficient is because I don't want to get into what normalization I'm using for the surface area measure, and so on. And so these things here that showed up on the previous slide, if I was looking specifically at a convex body, would indeed be intrinsic volumes. So I'm just restating that result before, that if I'm looking at a smooth convex body in odd dimensions, then the magnitude asymptotically looks to the top three orders like a linear combination of intrinsic volumes. And we might hope that that continues, but in work that isn't written up yet, but that Gimperlein and Goffing have told me about, they've calculated what the next coefficient here is, and what it turns out to be is a multiple of the integral of the mean curvature squared. So that's basically the Willmore functional of the boundary, and that does not give a valuation. It's not an intrinsic volume, so it stops looking like an intrinsic volume once we get past those top three orders. Okay, now I'm going to move back to L1, and for this I need to introduce a analogous idea of intrinsic volumes, which Leinster introduced. He introduced specifically in order to develop this connection with magnitude. So there are a family of things that I'm going to call L1 intrinsic volumes, and I'm going to write them just like intrinsic volumes, but with primes here. And an important point here is I'm going to be applying these not just to convex sets, but to a more general family of things called L1 convex sets. So here's a drawing of an L1 convex set. So I'm not writing out the definition, but the idea is that ordinarily convexity means if you take any 2 points in your set, a geodesic, which is a straight line for the Euclidean metric, that connects those 2 points has to remain in the set. So for L1 convex, I only require that 2 points in the set can be connected by an L1 geodesic, which works out to be a path whose coordinates are all monotone functions. So this is an L1 convex set because I could get from this point to this point in a way in which each coordinate was increasing monotonically, or I could get from here to here by having one coordinate increase monotonically, the other decrease monotonically. So this is a larger family of sets. And Leinster proved analogues of a lot of the classical results about intrinsic volumes for these. So in particular, VI prime is, up to normalization, the unique I-homogeneous valuation on compact L1 convex sets, which is invariant under isometries for the L1 norm. So this is a larger family of sets, which puts more restrictions on the kinds of things I'm looking at, but I'm allowing a smaller set of isometries here. L1 isometries are just translations and permutations and reflections of the coordinates. So it's just a much smaller isometry group. And so it's a little bit of a surprise that we end up with something so formally similar to the Euclidean context. And somehow these two things balance each other out in just the right way. There is a version of the Steiner formula where you might expect me to put the L1 ball, but actually I put a cube instead, and I get this kind of thing, which in particular says that if I was looking at a convex set, then comparing this to the general Steiner formula or the definition of mixed volumes, I would see that these L1 intrinsic volumes are actually special cases of mixed volumes with the cube. But as I said, it's important that I want to look at more than just convex sets here. I want to look at these L1 convex sets. And I'm not going to give the statement, but as I said, Leinster also proved versions for the L1 intrinsic volumes of a lot of the classical results, like Crofton formulas, kinematic formulas, Kubota formulas. So as I said, the reason these quantities, these L1 intrinsic volumes were introduced was to develop the connection with magnitude. So here's the main result. If I have an L1 convex set in L1, and so this means when I'm talking about the magnitude here, I am talking about the distance being given by the L1 norm, then I get this upper bound on the magnitude in terms of the L1 intrinsic volumes. And using that Steiner type formula, it's exactly equal to this volume here. And we get equality if K is actually a convex body. Now, on the one hand, this over here might look like the easier to understand upper bound, but I don't know a direct proof to get from here to here, even in the convex case. The only way I know how to do this goes through these L1 intrinsic volumes. And also this perspective of the L1 intrinsic volumes is going to be important for the application to come next. But let me just quickly sketch out the proof of this. The first is, as I mentioned already, we can easily say what a weight measure is for an interval. And here's one of the crucial places that the L1 norm is important. The L1 norm plays very nicely with the idea of weight measures because you're just looking at an exponent of a sum. And so we end up being able to just take products of weight measures in order to get a weight measure for a product. And that leads to this theorem being true with equality for boxes like this, parallelepipeds. And then we can use a tool from valuation theory, Grömer's extension theorem, to tell us that we can more or less explicitly describe weight measures for L1 convex sets that are finite unions of boxes. And then we use the fact that we can appropriately approximate a set of this kind by such sets. And these finite unions of boxes in general are not going to be convex, but they will be L1 convex. And so it's really crucial that we allow ourselves to work with that more general class of sets for the proof, even if convex bodies are what we're interested in at the end of the day. Okay, so let me say a few things about general subspaces of L1. So one simple observation we can get out of this is that we can estimate that upper bound for a convex polytope in terms of the number of vertices and its diameter in a way that makes no explicit mention of dimension, which is a handy fact. Another thing we can do, and this I'm not going to have time to really get into the details of, is if I start with any n-dimensional subspace of L1, there's a particular family of homogeneous valuations on E, and part of what's hidden in here is that the way they depend on E is nice in various ways, and in particular, it's plays nicely with isometries. So this only depends on E up to isometry, such that I get an upper bound in terms of these things. And so these are things that I think that this is some kind of hint that these valuations that show up are something that deserve to be called intrinsic volumes in this arbitrary subspace E, but this is very much work still in progress, so I don't have a whole lot to back up that assertion yet. But coming back to a point from before, either of these two corollaries can be used to show that if I have a compact subset of any finite dimensional subset of L1, then when I shrink that set to a point, the magnitude just goes to 1. I don't quite have enough to be able to say this is true for any compact subset of capital L1. In fact, I suspect that much is not true, but at least compact subsets of finite dimensional subspaces of L1 have this property. Now I want to go back to Euclidean space, and this is in a paper that appeared last year. If we specialize what was going on to Euclidean space, we get an upper bound in terms of the classical intrinsic volumes, but with this kind of coefficient here. And using an inequality that was observed by McMullen, I can estimate this all in terms of the first intrinsic volume, basically the mean width. And this is something that lets me say something about some infinite dimensional sets. So notice this is L2 without the n here. Basically, we can extend the intrinsic volumes to subsets of an infinite dimensional Hilbert space, and those for which the first intrinsic volume, and therefore all the intrinsic volumes are finite, is a set, as a class of sets that have been studied in the literature on Gaussian processes. They're called GB bodies. GB stands for Gaussian bounded. And I'm not going to get into why that name, but this is the first known result that says that certain infinite dimensional subsets of Hilbert space have finite magnitude and also have this property that the magnitude still goes to 1 if you shrink to a point. Then finally, my abstract claimed that there would be a new proof of Sudakov minoration. And so we'll finally come back here. So this upper bound here, if you look at what the coefficients are, we can prove that the magnitude of a compact convex subset of L2n is bounded by this function of the first intrinsic volume. So exponential of that intrinsic volume to the 2/3 power. And so if we just basically solve this for V1 and we use homogeneity to let ourselves have a little scaling freedom here, we get this lower bound on the first intrinsic volume. And as a corollary, we can almost immediately get from this Sudakov's minoration inequality, which is an important tool in asymptotic convex geometry and in the theory of Gaussian processes, which is this lower bound on V1 in terms of the size of an optimal epsilon net, basically. So I phrased it in terms of epsilon separated families of points. And the idea is we estimate the magnitude using a uniform measure on a collection of points, and we just choose the scaling here appropriately. And then this falls right out. I'll just end with a very brief observation that actually, if you go back to the original definition, or not the original definition, but the supremum expression, I said that magnitude could be given by a supremum of a certain expression over all signed measures on your space. If I only looked at positive measures and replaced magnitude with that quantity that was a supremum over positive measures, then this result would be equivalent to Sudakov's inequality. The fact that magnitude is allowed to also look at signed measures, which was crucial to proving this result in the first place, means that in principle, this corollary might be rather stronger than Sudakov's inequality, but whether it actually is in a useful way is, again, a subject of ongoing investigation. And with that, I am finished. So thank you very much for your attention.